Okay, all right. So in this module, let us understand how we can build a hardware for a current mirror circuit using two bipolar junction transistors. So here I have actually used the SPICE circuit simulator and the device libraries. So basically, I would click the new schematic right here, and then the screen gets open, and then I will click here the components where I will look for the components I want. So for example, let's say I want to find a transistor 2N2222A. This is the transistor I have. Or instead that is not found, then what I do is type BJT here, or maybe let's say NPN. I will type here NPN, and that's my transistor here. So I click here, you see that this is your NPN, and this is NPN2. So there are two kinds of transistors. So I click here NPN, for example. What's the difference between these two? We'll have to see. So let's say I click Q1 NPN, and then here it is Q2, right? And right click here, you see that this is a transistor. Polarity is here, but you can click here, pick new transistor. So this is 2N2222. This is the NPN transistor. You see that it has voltage between collector to emitter, VCEO, with base open is maximum 30 volt. Maximum collector current it can withstand is 100 milliampere, and then there is this SPICE model where you have a beta factor of around 200 here. So let me do that, and maybe here you see that. Okay, so let us click OK, and similarly right click here, right click this transistor, again click here and select OK. So these two transistors are there. Now what you do here, you have this transistor, why not click edit and see if you can rotate that. Yeah, just like Control E. Yeah, and then maybe Control R. Yeah, you see that now I have adjusted and put up this transistor in this fashion by using rotate and mirror. Then what I do and want here is, let's say I want DC voltage supply. So let's say VDC, I type here, or let's say voltage V, maybe voltage, yeah, VOL, voltage source. So I take voltage source somewhere here, escape, then press right click on this, add a DC value of 5 volt, series resistance maybe 10 ohm, because maybe let's say a practical voltage source, click OK. Then you click here, this is your ground, put up here, then you have this symbol somewhere here, then you need the label also, right? So what you can do, click component again, then let's say VCC, no, or VDD, no, or simple, let's say voltage. Okay, this here. Then what you can do here, you want register, click component again, then type RES. So that's your register. Click OK. put it here. This is R1. Press escape. Right click. Let's say how much current you want to actually flow through this resistor and through the collector of this transistor Q1. It depends on the value you choose. So let's say you choose uh, around 2K. So this is, let's say, 2K. Click over here and then you're all set almost. So click the wire here, F3, make connections. Then let's say you are here, somewhere here, okay? And then press escape, press the space bar so you get the circuit on your screen. Again, click wire, make the connections here. You see now how I am doing this. And here, you keep it open for a while, let's say here. Then again, come here and make the circuit complete. So let's say you put it here, somewhere here, and press escape. Again, select wire, complete the circuit. Now it's time to label the circuit, but before that, you have to do this one, and then for transistor Q1, collector and base are shorted. Press escape. So you see now your circuit is what it shows, a current mirror circuit. So now what you do here, click wire again, make a wire here, press escape, then again click here and click and then one. So this is the junction you got here, then right click here. This is the highlight net you can see, but before that, right click and label it. So here you can label it to be ground or common or what the port is. So let's say I call it VCC, that is my supply voltage. Say this is the input, or you can select none because this is not the input signal coming to the circuit. Instead, it is a voltage supply. So let's say, and I place it here. Similarly, I want to place it here. So at these two nodes, I am actually getting this supply voltages here. So if I right click here and highlight, click a highlight, you see that this is the 5 volt VCC. That is the 5 volt DC voltage is coming over here from this voltage supply. Now, we know that this is the transistor Q1. Again, right click, and if you click pick transistor and see this spice model of this transistor, then what I am interested in here is the beta factor is 200. Will not go detail into the theory of this. And then I'm interested in knowing the base emitter junction voltage of this. The manufacturer is shown here. So do I see the junction voltage? That is the turn on voltage of this PN junction transistor. 800 milliampere maximum current and maximum voltage across collector to emitter with base open. Anyways, so with this done, let's say I have 5 volt divided by 2K. So that's the 2.5 milliampere current I am expecting to flow through this transistor. That is the collector current flowing through this transistor, isn't it? Okay, so yeah. So how do we know that? How do we measure or how do we know that? So we can do the basic DC analysis for that, but this node is open. So we cannot actually let it open. So what you do here is just have another resistor from this, put a load there. So let's say it is 100 ohm value. Let me just do one thing and undo again a resistor, place it here somewhere and then have a wire connection. Okay, and then maybe here and here also I would make this, let's say, this one. No, I don't want to move it. Instead, I want to copy. So how do you copy that? Duplicate F6. So just say you are putting it here as well. So you here you also have 5 volt, but now we have to see the current in transistor Q1, how it gets mirrored in transistor Q2. So for that, right click, put the value of this to be 100 ohm. Okay, so click here. That's it, all set. All right, so what we can see here, the base emitter voltage of this transistor is approximate 0.7 volt. So the current flowing through the resistor R1 and through the collector of the transistor Q1 is the voltage 5 volt minus the base emitter junction of this transistor VBE, which is 0.7 volt, divided uh, divided by the value of this resistor will be the current flowing through this branch or the current flowing through this transistor. Okay, so that comes out to be 5 minus, how do we calculate that or how do we do that? It's just like you have to pause. Okay, so what we can understand from this complete circuit here is you have 5 volt here, and then there is the current flowing through the resistor R1, also through the collector of this transistor Q1. Since the collector and the base is shorted, we see that VCE of this transistor Q1 is equal to VBE, and VBE is 0.7 standard voltage. So if you want to know the current flow through the resistor R1, and hence the collector current of transistor Q1 is this voltage minus this voltage drop, that is VCE, or in other words VBE, divided by the value of this resistor, that is 2 kilo ohm, and that comes out to be approximately 2.15 milliampere. That's the current flowing through this branch right over here. Now, assuming the Q1 and Q2 are perfectly matched pair, and that's what is the prerequisite for building a current mirror circuit, and as therefore the base emitter voltage, that also means the base emitter voltage of the both transistor are exactly 0.7 volt. If we assume here it is 0.7 volt, then for this also 0.7 volt. We also assume both transistors are same. It means their base currents, collector currents, their beta factors all are same. There are no manufacturing tolerance ideally, but it would not be the same in practical situations. So we assume in theory they are same. Therefore, the voltage of base emitter of the transistor Q2 is also the base emitter voltage of Q1. That makes the transistor turn on, and then this current is therefore, the current in Q2 is therefore is equal to the current in Q1. Now, to measure this current, we are basically connecting a load of 100 ohm value here. And since the same current, that is approximately 2.15 milliampere flowing here, when we said that that got mirrored into R2 now, so the voltage here across Q2, that is the output voltage, is nothing but 5 volt minus I times R2, is the voltage. That comes out to be approximately 4.785, and that's the condition also in order for the circuit to work correctly, that the voltage across Q2, that is VCE, should be greater than the voltage of base emitter of the transistor Q2. That's how the current mirror works. Now let us see how this works. So for that, we'll have the basic analysis here. So what you do, click the right one, and then let's say go to tools, uh, control panel, maybe here. No, not the control panel. Go to spice netlist here. That gives you a spice netlist showing how components are connected. You have to set the spice deck now, right? Spice directive, spice deck. So how do you do that? Edit simulation command here. And here you select this DC operating point analysis here, which will compute the DC operating point, that is treating capacitances as open circuits and inductances as short circuits. So that's the syntax.op. Click OK, place it here, then go to simulate, click run. Boom. And here you are. So now have a look at the current of the transistor Q1, that is 0.0021, that is approximately 2.119 milliampere. Then come here Q2, 0.00220, that is approximately 2.20, so which is pretty close to current in Q1. Both collector current IC and IC of transistor Q1 and Q2 are approximately same, right? And that's how we see the current through IR1 and IR2 here. And that is how you basically see that. The VCC is 4.95 because we assume theory 5 volt, but due to series resistors of 10 ohm, it is showing 4.95 volt, right? So our calculations are close to what we are seeing in the circuit right here. And then that is the voltage at node 001, which is here. This is the node 001 across the transistor Q2, 4.73 volt, and voltage at 002, that is the base emitter voltage, right? This node, right? And that is how you basically see that. If you want to avoid this confusion, just label the node. Let me show you. Right click, label it. Let's say the base, call it base. And maybe you can say this is the port. Let's say you are labeling it base. Then here maybe you call it, let's say VO, maybe output. That's how you basically take this output here. Okay. And now if you just uh, don't have the value of the series resistance because you assume ideally 5 volt, then you save and then click run again. Now you see the results. Have a look at the voltage at the base here. Now you see voltage at the base is 0.67. In theory we said it's 0.7 volt. Output voltage VO 4.77, which is the voltage across Q2. VCC is 5 volt. And now look at the current IC in Q1, 2.14 milliamp, and IC in Q2, 2.22 milliampere, close. IR1, IR2, similar. And that is how you can see that this circuit works as a current mirror, where the current in transistor Q1, due to the properties of the transistors, assuming them to be are exactly equal with low manufacturing tolerances and defects, the current in Q1 gets mirrored in Q2. Now let us see how this circuit can work in hardware, actual hardware. Okay. So hope you found this model useful. Stay tuned for more engaging content like this. All right, so here is a hardware realization of the basic current mirror unit that we have tried to build using the two bipolar junction transistors. So as you can see, these are two BJTs, and we assume that their manufacturing has been in such a way that they are they are exactly identical to each other. It means their specifications, the device properties are matched with, ideally in theory, 0% variations. For example, their collector currents are same, their DC gain factor or beta are same, their VCEO, that's the voltage between collector and emitter with base open, they are also equal. That is what all these parameters we can verify or see from the data sheet. And also the base emitter junction of these two transistors are also matched, approximately 0.6 volts, or let's say 600 millivolts. So having said that, if you see that the circuit is being shown to you and exactly as shown in the schematic, these transistors and the associated components are assembled on the breadboard. This LED is extra here, that is just to indicate whether the current that is being generated in the reference transistor, or say the reference part of the circuit, which is the left side of this one, that is then get mirrored into the right side of this current mirror unit. And if the current is flowing, the LED glows, and that's the indicator that we have or we have not mirrored the current. So what is to be seen here is whether we have actually managed to mirror the reference current in this transistor into the output transistor. So you see that the value of this resistor is around 4K, or let me repeat that again, or let me measure it, and then we can see that. Okay, so what is to be seen here, the value of this resistor is 2 kilo ohm, the value of this resistance is 100 ohm actually. And we will now measure the current that is being generated by this part of the circuit, or in this part of the circuit, and then we will measure the current that is being mirrored into this part of the circuit, and both should be identical to each other, and that's what we exactly look for. Okay, so what you need to first do is to kind of let me see, press the button here, switch here, and with this we will see how much current is generated. So here you see that the LED has been turned on and the LED is glowing. It means the circuit is working, and what is expected is that the current would be around 2.5 milliampere, because we are sourcing 5 volt supply DC volt, and as per Ohm's law, 5 volt divided by the value of the resistor sets the reference current into this part of this unit of current mirror. So 5 volt divided by around 2K, so let's say 2.5K, but more precisely 5 volt minus the VB voltage drop across the base emitter junction of this transistor, let's say 4.3 volt, because 0.7 approximately would be the drop across the base emitter junction of it. So 5 minus 0.6, let's say precisely, will be 4.4 volt divided by 2 kilo ohm, so around 2.2 milliampere should be the current, or 2.1 milliampere should be the current approximately. So we have to measure it. So let us set the voltmeter, the multimeter, to be in the current range of this transistor. Let me do that. So here is the setting of the multimeter in the ammeter mode. The knob has been put up to 20 milliampere. Okay, and now let us measure the current here and we'll see what's the current look like. Okay, so let me just put up the meter like this, and before that I want to measure the current, and I have to put the ammeter, that this multimeter acting as an ammeter now, and I want to put it into the series branch of this part of the circuit. And to do so I have to first switch off the circuit here, and then make sure I open the circuit here. Okay, break the circuit, make the part of the circuit, and then put an ammeter there. So what I do here is, let's say I just connect it somewhere here, the resistor, and now then I can insert the ammeter. So switch it on now. Okay, and then put an ammeter in series with this branch of the circuit, so between 5 volt and the resistor end. And what I see here, approximately, if I see, the circuit gets closed because I have inserted an ammeter, and exactly the current value is 2.15 milliampere, what we predicted in theory. The negative sign indicates that I have to reverse the lead of the multimeter. Okay, because the positive the red probe is connected to the resistor end, and the black probe is connected to the plus pin of the 5 volt. So therefore it's a negative sign. If I reverse the lead, that's an exercise for you. You will see the positive reading on the meter. So minus 2 point, or let's say plus 2.15 milliampere is the current. Again I remove it, and then I switch it off, get the resistor back to its pin originally it was, where it was, and now I have to measure the same current, whether it is being mirrored into the right part of this part of the circuit or not. To confirm that, I will now insert an ammeter in this part of the circuit. And to do so, we have to understand where to put an ammeter here. So what we can do here is break this branch of the point of the resistor, connect it somewhere here, and then now you broke the circuit here, and now switch it on and put an ammeter now, and you see the reading, and the circuit gets closed, and you see that 2.27, a little higher. Okay, we measure to the left part is 2.15, and here it is about 2.32. So difference is about 0.15 milliampere. So that much is. So why the output current is higher is a question for you. Just write that into the comment section. Hint is the output resistance of the circuit, right? And there is this minimum voltage across the output part of the circuit that you have to maintain to keep the circuit working as a current mirror. So that's the way you can see. Again, get back to your original connection here. I should have first switched it off and then make the connections, but you can make sure you do so. And now what else you can measure is the base emitter junction voltages of these transistors. So for that, set up the voltages, set up the multimeter into the DC part, let me show you. Let's say I have set it to 20 volt, and then now I don't need to break the circuit because I'm measuring the voltages. So what I can do here, base emitter voltage, the base is positive and the emitter is here, and let me show. But here I make a possibility of shorting the lead, so I have to make sure that I am accurate in doing that. So here is the base connection possibly, and you see that this is the forward voltage junction, forward voltage drop of around 620 millivolt of this transistor. And similarly here also you can make this around 620. So these are exactly identical. Okay, so this is how you can actually measure it, right? How about what else you can measure? The base and the collector of transistor Q1 here are shorted together, right? And therefore this VB and VC of these transistors are equal. Then exercise for you would be just to make sure that you have this one. So now you can actually see that if you remove the LED, for example, and then try to measure the current in this branch, so possibly you can see if there makes any difference. So for example, switch it off here first, remove the LED, and instead just have this resistor connected to the collector pin, then break this point of the circuit so that emitter can be put in there. Now set the meter to the emitter gain, emitter range. Here let me show you, set to 20 milliampere, come back, put it here, switch it on, place the meter there, try to measure the current again, and now you see that the current has increased. It's now 2.52, earlier it was 2.32 something. Okay, so it is because of the resistance decreased in the circuit, because LED offered some resistance earlier. So you just switch it off. Maybe it's better that you can have this resistor connected here. So put the LED there and have your circuit worked as before. So have to make the connections, and that's how, this is how you can see this. So now how about to match the measurement results or the actual results that you see here for the currents? How about you try to do that in the simulation? Okay, and try to see try to build a model of this circuit in the schematic simulation. So we'll use the spice simulator and we'll see how it works. Okay, so try that. All right, so as we've just completed the hardware part of the circuit, and here you can see now, if you see that the resistor is 2K, the transistors are the one that we have used in the hardware, VCC of 5 volt, resistors here is 100 ohm, and of course the current we measured here in this branch was around 2.15 milliampere, and here in this branch was around 2.32 milliampere. Okay, so with the dot op analysis, let us press the simulation button, and again here are your results that you can clearly see. First is the voltage at node B, which is the VBE of both these transistors. Okay, the voltage at base with respect to emitter, that is 0.67, that is 675 millivolt, and we measured around 620 millivolt. So that's the difference. Possibly it because of the measurement inaccuracy, because we use the low cost uh, uh, multimeter, first reason, and second is of course the hardware results always differ slightly with the simulation ones. If you see or understand any other reason, you can write that into the comment section. Now look at this voltage, output voltage, that is the voltage at collector of output transistor with respect to emitter, that is around 4.73 volt, 4.77 volt. VCC is 5 volt. Now here's the main, that is the current through the collector of this transistor, which we measured to be 2.15 milliampere, and here is 2.14. So it's exact, pretty close match. Okay, 2.14 milliampere. Then come here, IC2 of Q2. We measured 2.32 milliampere or 2.31 without the LED, and here in simulation is 2.22. So there is some difference here, but it's still of the same order in magnitude. So that's how. Similarly, IR1, IR2 are same as IC1, ICQ1, and ICQ2. So this is how you can actually see that the difference, the simulation and the measurement or the taste of this basic unit of current mirror circuit. Okay. So hope you found this module useful. If you did so, share it with others for wider reach and stay tuned for more engaging content like this. Till then, wish you happy learning.